think we can start. So good morning, everyone. My name is Francesco Petruccione. I'm the director of NITEX, which is our National Institute for Theoretical and Computational Science. So thank you very much for joining us on a Saturday morning. Today it's a kind of event a few days before the actual celebrations of the events, but because we target it at learners who during the week are busy at school, we thought we can try to organize it on a Saturday morning. Yeah, so the event that we want to celebrate is Quantum World Day. Yeah, and you have probably all heard about quantum stuff many times in your academic career, and the aim of today's event is to give you a brief insight on what is quantum is all about and why people are so excited about it these days. Yeah. So we have let me share my screen so that we can quickly go through the program. Just a second, I'm here. Here we go. And now let me share it properly. Okay, so we have a very exciting program for the day. Yeah, I will make a few introductory remarks in a second. Then we have Dr. Garry Kemp, who will briefly explain to us what is quantum, yeah, on very generic terms. Good morning, Garry. Thank you for being with us this morning. Then it will be my turn again, so you'll see a lot of me this morning. I will try to explain to you what is quantum computing and why people are so excited about it in the high-tech world, and and also maybe address what opportunities are out there for young people like yourselves. After that, Dr. Yaseera Ismail, who is working with me at UKZN, she will give us some insight about quantum communication, which is another quantum-enabled technology that has the potential to shape the future of the internet. And finally, but not last but not least, yeah, Betony Adams, who is a PhD student in my group and who has been working for several years on topics related to quantum effects in biological systems, will give us a brief introduction to quantum biology. Yeah, so that you will also see that quantum technology is not only about gadgets, but it can also be about living beings, yeah, like ourselves. Yeah, so we have also quantum stuff going on inside us. Yeah, and finally we made we allocated some time for questions and conclusion. Yeah, so please, you are most welcome to make use of the Q&A facility to ask questions at any time. And of course, at the end, we will still have a little bit of time for questions. Yeah. So let me start. Okay, just checking the time with some very generic remarks. Yeah, about why there is a hype about things quantum. Yeah, and probably the at the core is that people are very much worried about the future of computing. Yeah, every time you buy a cell phone or a laptop or a desktop computer, it becomes faster, more powerful. There is more memory. Yeah, and that's because of the fast pace at which technology evolves. And at some stage, we will hit the limit where we can't build computers anymore with the current technology. We need to do a kind of a jump to another technology that allows us to do more, yeah, faster, better, and so on and so forth. Yeah, and another very interesting aspect is that you probably heard a million times by now the role that artificial intelligence and machine learning play in the famous fourth industrial revolution. Yeah. And one of the core reasons why artificial intelligence and machine learning is so powerful these days is, of course, because the underlying hardware that is used is getting more and more powerful. Yeah? you know, quantum machine learning was around for many decades, yeah. But computers were not fast enough to allow it to do what it's able to do these days, yeah. And quantum devices are a kind of gadgets that can speed up calculations for machine learning and artificial intelligence, yeah? So that the applicability of artificial intelligence and quantum technology goes essentially hand in hand, yeah? So when people think about the future of computing, yeah, there are essentially roughly 3 approaches that you can follow. Yeah, there is the traditional one, they call it the classical one with the bits that you know, these objects that are 0 and 1, and you can add them in a binary way, and probably learned it at school, which is essentially the combination of mathematics and information. Yeah, the bit is the unit of information. There is something, there is nothing, there is a current, there is no current, the switch is on, the switch is off. Yeah. Another approach is to model computers on how our brain works, yeah, by taking inspiration from biology. Yeah, you probably heard about neural networks, couple it with concepts from information theory and build neural computers. Yeah, this is another approach. The one that looks very promising at the moment is the quantum approach, where you use quantum physics, yeah, couple it with concepts from information, and you create other objects that are relevant for information theory that the physicists call quantum bits. Yeah, and later today we will hear all about them. Yeah. So what has been going on in the last 50 years or so, yeah, is that the theory of quantum mechanics, and Dr. Garry Kemp will explain it to us just now, yeah, and the theory of information science, yeah, merged into what becomes now quantum information science. Yeah? And quantum information science has essentially 3 pillars. Yeah? There is quantum computing, quantum communication, and quantum metrology. Yeah? The metrology is the science of measuring things. Yeah? and what we will do today, we will give you an insight in all of these. Yeah? This quantum business started more than 100 years ago. Yeah. And some people call it the first quantum revolution, when people starting observing phenomena in nature that Newton's law couldn't explain. Yeah? And it started with Max Planck, Albert Einstein, who, for instance, who came up with a theory that light is also a quantum particle. Yeah, today we call it photon. Yeah. And so on and so forth, yeah. And until, you know, the highlights were almost exactly 100 years ago, when people like Erwin Schrödinger, Werner Heisenberg formulated the theory that today we call quantum mechanics. Yeah. So you see, it started long ago. Yeah. But it became very interesting for technological purposes, the ones that we discussed today, only much later. It took a long time to get to where we are today. Yeah, and the first one who had somehow the inspiration that the quantum world could be useful for advanced technological application was Richard Feynman, who won the Nobel Prize several years ago. Yeah, and he realized that since at a fundamental level, all natural phenomena are quantum, yeah, in one way or another. Yeah? Then if we want to simulate this quantum world, the best way will be using computers that operate around following the same rules as the natural world. Yeah, and today we call them quantum computers. Yeah? And at the beginning of the early year 2000, yeah, people starting mentioning a second quantum revolution, yeah, where people really start using all the spooky properties of quantum mechanics that Garry will share with you just now, yeah, to actually do things, yeah, not to be scared about them, but actually to use them as resources. Yeah, so all the crazy things that quantum mechanics does, yeah, can be actually used to do things. Yeah, so and that is what today is about. Yeah. So that you see, this is just a short timeline of what people call now the second quantum revolution. Yeah, and it started maybe in the 80s with the vision of Richard Feynman. Yeah, and And it continues, let's say, until today is where the first quantum computers have been built. Yeah, but essentially, what triggered this second quantum evolution is that only in the 80s or 90s we developed the technological ability to manipulate single quantum objects. Yeah? You know, since at the times of Einstein and Schrödinger, people thought of atoms and molecules, electrons and photons, yeah, but nobody had really the technical ability to manipulate a single atom, a single electron, a single photon. Yeah, so those are things that started only in the 80s, in the 90s. Yeah, and this triggered the second quantum revolution that everybody is talking about today. Yeah, and so you see, you heard a lot about the industrial revolution, yeah, that started a couple of 100 years ago with the invention of steam engines and things like that, going over to first electronic devices, telephones and things like that, coming in the 80s with computers, and today we are in this experiences, this fourth industrial revolution with all the fancy things that robots, artificial intelligence, machine learning can do for us. Yeah, and parallel to this fourth industrial revolution, there is the second quantum revolution. Yeah, and what people believe is that we will need the second quantum revolution, or the technologies emerging from the second quantum revolution, to achieve the goals of the fourth industrial revolution. Yeah, so this is where I think also the opportunities for young people lie. Yeah, because you want to establish yourselves in this context. Yeah? So maybe just to conclude, yeah, you know, the first quantum revolution, yeah, that I mentioned 100 years ago, yeah, gave us also important technologies, yeah, that we can't live without anymore. Yeah, for instance, the transistor is a consequence of quantum mechanics, yeah? Or lasers that you use every day. There would be no optical communication without lasers, yeah? Or you couldn't check out quickly at the supermarket if there were not those red laser scanners, yeah, that read the barcode on the products that you buy, yeah, and so on and so forth. And today we have other technologies, yeah, quantum computing we mentioned, quantum communication, quantum metrologies, and these are the key technologies for the fourth industrial revolution, yeah, because they allow us to measure data more precisely, to transport data more and share data more securely, yeah, and to process data very fast. Yeah, so these are the promises of the second quantum revolution, and is what the fourth industrial revolution needs from us. Yeah. So thank you very much. This was my small introduction to our topics. And I will now, sorry, I'll stop sharing my screen. I will now ask Dr. Garry Kemp to start with his introduction on what is quantum. Yeah, and please, if you have questions, as I said, make use of the Q&A facility, and we will attend to your questions. Yeah, Garry, please, you're most welcome to start with your presentation.
Okay, so good morning. I'm just attempting to share my screen, so just give me a moment. I have one or two preview files open, so it's a bit hard to tell exactly which one is which, because let's just see. So just give me a moment. I apologize. Let's close that. Okay, so let's try share now. Okay, let's go with this guy.
Sorry, it looks like we lost Garry. Okay, I don't know. Let's wait 10 seconds to see if he comes back quickly. Otherwise, maybe we we move on with the next talk, and we come back to Garry when he joins us again. Let's see a second if he, here we go. Here he comes again.
Sorry, I'm back. I'm back. I just had to try and, okay, good.
Okay, fantastic. Now we can see your screen, Garry. Maybe you want to go on full screen mode.
Yeah.
Perfect. Excellent. Thank you very much.
Okay, just as a last check, can you see my slides changing?
Yes, perfect.
Okay, fantastic. Okay, so good morning, everyone. Sorry for the delay. Thank you to Francesco for organizing this wonderful event. And I think, yeah, so the idea for the next 15 or so minutes is to, I guess, to try and allude to at least the first quantum revolution that Francesco spoke about. So yeah, I'd like to try and give at least a flavor of some of the key ideas that went into the key ideas that form part of quantum mechanics in the 20th century. So I'd like to start off with a very key experiment, a very crucial experiment that was done. It's known as the double slit experiment. So the idea here is that if you think about firing classical objects like golf balls or tennis balls at this particular setup over here, so there's a barrier, and then in this barrier, there's two openings, or there's two slits, and this object can then travel through either one of these and then onwards to strike the back wall. So you can do this kind of experiment with golf balls or tennis balls, as I said. And if you imagine what the result will be, if you do this experiment over time, you'll see a buildup of these two vertical bands corresponding to, each opening or each slit here at the front over here. So this is what you'd get if you would do this kind of experiment. You can now ask yourself the same question. Now, what would happen if you now decrease the size of these objects? So maybe they're not golf balls or anything like that. So maybe they're small pebbles or small little marbles, and you continue, or you repeat this experiment. You will see very, very similar results, right? However, now the surprising thing, if you repeat the same experiment, not with normal everyday objects, but with, let's say, electrons, right, sort of quantum particles, you'll see a very different behavior, right? You'll see a different pattern that builds up on the back detector, or the back wall. So instead of just seeing two vertical bands, you'll now see a whole series of light patches and dark patches over here on this back wall. So here are some images from actual experiments that were done. So these are electrons being fired at this double slit experiment. And over time, you see these little dots here on the top left screen. These little dots correspond to, an electron striking that back wall or that back screen. So each little dot corresponds to one electron striking that screen. And over time, as the electrons build up and build up and build up, here at the bottom right, you can clearly see a very striking interference pattern, a very striking pattern here of light patches and dark patches. So yeah, this baffled people for a long time. And this was a very, very surprising effect that happens when you deal with these subatomic particles. So you might ask yourself, how can we explain such a phenomenon? Well, there is something else from nature that produces very, very similar behavior. And what we see is that if we shine light waves on a very similar experimental setup. So here on the left, you have plane waves that are incident on this barrier over here with these two openings. So what happens is that you get these two wave fronts that emerge from these two openings. And these wave fronts, as they propagate towards the back, they will interfere with each other. So there'll be some regions where there'll be constructive interference, and there'll be some regions where there's destructive interference. And that will correspond, that corresponds to these light patches and these dark patches here, these bands over here. Just from a mathematical point of view, if you want to gain some insight into what's happening. So here in this top picture, I'm adding two waves together. So there's a sine wave and there's a cos wave that's been shifted by 90 degrees. So it's actually just the same wave, right? So they've got this orange curve over here, represents the sine and the cos wave. It doesn't look like there's two curves, but I mean, they're actually the same curve, but there are two curves there. Now, if you add them together, you're going to have what's called now constructive interference. They're going to add to each other. So the amplitudes increase and everything like that. So this is an example of constructive interference. The situation here at the bottom, if I add the sine function with another sine function that's out of phase, right? That's out of phase. What's going to happen if I add them together? This is an example of destructive interference. So if I add the orange curve with the blue curve, they'll cancel each other out exactly. So the net result will be this green flat curve, this flat line over here. So what scientists concluded is that there's a very wave-like quality to electron behavior, right? So the middle picture here is what we see classically with normal everyday objects. The top picture is what happens with waves, and we see very similar interference pattern with what's happening at the bottom here when we do the same experiment with electrons. Now, so we have this wave-like property or this wave-like nature to particles. Also, so much so that we describe or that there's a mathematical object called a wave function specifically to describe the behavior of these quantum particles, right? So now there's a wave function to describe the behavior, and over many, many years, and even to this day, not everyone agrees on the precise nature of this wave function. And this picture over here is Niels Bohr on the left, and Albert Einstein on the right, and it doesn't quite look like it, but they are engaged in a fierce debate over the nature of the wave function itself. Okay, good. So let's explore just briefly some consequences of adopting this kind of picture. So on the top over here, I have a wave function. It looks very nicely spread out. And if I ask you, what is the wavelength of this particular, what is the wavelength of this wave? Well, that's a well-defined question. You would tell me, well, obviously the wavelength is just the distance from the one peak to the other peak, right? Now, in wave mechanics and quantum mechanics, the wavelength is related inversely to the frequency of the wave, and it is also related to the speed of the particle itself, right? So the wavelength, you can easily see what the wavelength is. So you know the wavelength, you know the speed. But if I ask you, where is the particle in this top picture over here? Well, then suddenly it's not so clear, right? You would say, you might guess maybe the particle is all the way to the left. Maybe it's somewhere there in the middle of the graph, or maybe it's somewhere on the right. It is not clear. Whereas at the bottom picture, so let's look at the bottom picture now, we have a highly localized wave packet. Right now there, if I ask you, where is the particle, you would tell me, well, it's in that little localized region over there where the wave function is not zero. Okay, so there, the position of the particle is well defined, or it's much more defined than in the top picture, right? However, if I ask you what is the wavelength, well, then now that is not a clear, that's not clear anymore. Right? So at the top, you know the speed of the particle, but you don't know where it is. At the bottom, you have an idea where it is, but the speed is not determined. So in fact, there's a quantum mechanical rule. So how do we go from the wave function to predicting where the particle is? So if you take that wave that I had in the previous slide and you square the amplitude, right? You get a picture here that looks what it looks like at the bottom. And then this picture at the bottom here are now the actual probabilities of finding the particle at a particular position if we were to do the measurement. All right, so that's a quantum mechanical rule. Anyway, so it really does seem like uncertainty is a fundamental property of nature, right? So this equation that I've got, this is the famous uncertainty principle. So it basically tells you that, if you take the uncertainty in the position and you take the uncertainty in the speed or the momentum of the particle, their product has to obey a particular inequality like this, right? So you can never know the position and the momentum with, infinite accuracy at the same time. So it's a strange world, what's happening in the quantum, in the quantum domain. In the quantum world, there's all these wave packets and wave functions going around. And what we see, right? We see in our everyday experience, we just see particles, right? And the barrier that seems to separate the two is quantum measurement, right? So, people use the terminology of collapsing of the wave function and all of these strange kinds of things. Another very interesting phenomenon exhibited by quantum particles is this idea called entanglement, or what some people have called spooky action at a distance. So what's happening here is that we've got two waves, right? Two wave packets, one on the left, one on the right. Okay, so say the one on the left has this property called green, right? Whatever green is, that particle on the left has it, right? And the particle on the right has the property red. Okay, so one is traveling from the left to the right, and the other one is traveling from right to left. Now they come together and they interact in some particular way, and they build up correlations, right? It's possible for them to build up correlations to the point where they become entangled, right? Or what's called entangled. So now neither particle is either red or green. Instead, we have a wave function, what I've called capital Psi here, that describes the total or combined system. All right. So now each of these particles goes off on their merry way. Maybe perhaps now they could be separated at great distances to each other. So now let's say maybe we have Alice over here on the left is in possession of one of these particles in her particular laboratory. And we have old Bob over here on the right. And Bob is in possession of the other particle in his lab. Now, you might ask yourself the question, what happens when either Alice or Bob performs a measurement on the particle that they've got? So let's say Alice here on the left performs a measurement. Alice wants to know, if I do the measurements, will I get green or will I get red? Okay, so let's say, for example, Alice does the measurement and Alice finds the property green, right, in her lab. We know, right, we now know instantly and almost instantaneously that if Bob were to do the same measurement, we know immediately the outcome of Bob's measurement, right? We know if Alice gets green, Bob will get red. Or if Alice were to do the measurements and Alice gets red, we know Bob will get green, right? So that's the idea. Now, you might ask yourself, what is happening at the level of the wave function, right? So did Alice's measurements instantaneously affect or have some kind of influence or collapse of the wave function on Bob's side, right? So these are questions that puzzle many people. And this is really, a real fascinating aspect of quantum behavior. So there's definitely a very non-local aspect to what's happening here with entanglement, right? So remember, these particles can be separated at immense distances from each other. So maybe the one is in, dramatic example, the one particle could be in one galaxy, the other particle could be in a completely other galaxy, and this effect would still happen. So you might ask yourself, does this mean that we can send information faster than the speed of light? Does this mean faster than light communication? Is Einstein's theory of relativity, is there a violation there? Well, it turns out that not so much. We can have non-locality or non-local aspects of physics and relativity coexist quite nicely. And there's nice, elegant, and efficient and elegant explanations to explain all of that. But this is really a fascinating aspect of quantum physics. Another phenomenon, the last phenomenon that I'll outline, is something called quantum tunneling. So another amazing thing can happen. So we've got a wave packet or a wave function here on the left. So I'm looking at the top picture, and let's say that it's moving towards a barrier, right? So it's a wall, a concrete wall, or some kind of barrier. Now, when the particle is in the process of, interacting with the barrier or bouncing off the barrier, in this wave function description, you see at the bottom picture here, across the barrier, the wave function will start to decay very rapidly, right? Quite rapidly. However, it is possible that a small little bit of the amplitude could make it through to the other side of the barrier, right? So that if we were to do now a measurement of the particle's position, we want to know where is the particle's position, there's a very small probability that we will actually find it on the other side of the barrier completely, right? So, this is a little bit like, if it's a hot day and you pour yourself a glass of ice water, So, pretty much the opposite of the kind of day that's happening in Joburg right now. But you pour yourself a glass of ice water and you give it a nice stir, and you see all the ice blocks, rotating in your glass, and you see an ice block heading towards the edge of the cup, and normally you would expect it to bounce off, and continue circulating within the glass. It's a little bit like, all of a sudden you will see your ice block appear on the other side of the glass and then fall onto the table on which the glass is resting. So this is completely bizarre, right? But in the quantum world, this kind of stuff actually does happen, right? This has profound implications on modern day computing, or on many aspects, and one of them is just modern day computing. So what happens is also what Francesco alluded to, that computer chips nowadays, they're getting smaller and smaller and smaller, right? So what's actually happening is that the wires in these chips and in these circuits, they're getting thinner, they're also getting smaller. So this becomes more difficult to maintain precise control over the flow of each individual electron, right, that might propagate through these wires. So it gets quite difficult, or we're getting to the point where it might become impossible or very difficult to maintain, a steady current within these computer chips. So a possible solution, which everyone is quite excited about, is quantum computing. So I'm sure later on in talks by the other members of the panel, this will be explained much more elegantly and efficiently than what I can do. But here are some pictures, just showing what some quantum computers can look like. So just very simply, what these machines do, or what they're capable of doing, they're using the laws of quantum mechanics, manipulating these wave functions that we've been describing to perform computational tasks that could outperform the same tasks on a normal computer, right? They'll be faster, they'll be more efficient. At least this is the hope for quantum computation, right? So there's all kinds of algorithms and computational tasks that people have discovered. So there's the factoring of integers into prime numbers. So, just very simply, if you want to take a large integer and you want to factor it into its product of prime numbers, the best classical algorithms run, something approximating exponential time. So that's so the larger the integer gets, at some point it becomes almost impossible for any computer that we have nowadays to actually perform this factorization. So this is here is a mathematical representation of this factoring algorithm that this person over here, Peter Shor, has discovered. So, what's happening here on the left, this little sequence of zeros and ones, these are qubits. And what these are basically just those little wave functions that we talked about a few minutes ago. Anyway, so this is a mathematical representation of a quantum circuit designed to do this particular factorization. And just very simply, a very simple idea is that, as opposed to your algorithm running in exponential time, which would be the case on a classical computer, the hope is that, and is the case for this factoring algorithm that I've described here, the hope is to design these quantum algorithms that instead of running exponential time, they will run something like polynomial time, right? So this number n over here, this is telling us something about the size of the system, the number of qubits or the size of the integer, that kind of thing, all right? So this is at least the hope. So where to from here? There are many interesting questions and many open questions and further directions to go to expand on what I've just said. And this is now the ideal place for all of you out there, for young scientists, to step up and get to work and start solving problems. So yeah, with that, I hope I haven't gone over time, but yeah, thank you very much, everyone.
Yeah, thank you very much, Garry, for this very nice introduction to all things quantum, and also for thank you for a little preview of what comes in the next section of our webinar. Yeah, I think the next section is about what is quantum computing, and Garry already gave you a little taste. and it will be now up to me. Sorry, I just need to find my presentation. Here we go. To add a little bit to what Garry has already said. Yeah. So what is quantum computing? Yeah. Here you see a cartoon that produced by the gentleman whose name you see on the bottom right corner, Dominic Walliman. Yeah. That summarizes a little bit all you need to know. Yeah. First of all, there is this discussion of classical world versus the quantum world, and Garry explained it very nicely. Yeah. Then we have the efforts to develop algorithms for these quantum computers, because they operate according to different laws from the PC in which you are watching this webinar. Yeah. We need to find application, but most importantly, we need to find the hardware to run this fancy algorithm to get the speed ups that Garry envisioned. Yeah, and there are very different technologies. Some companies bet that superconducting devices will be the technology that is needed. Other companies think that maybe it's optical photon-based technologies that lead to the aim. Others are playing around with ions, and others with diamonds. And so there are very different technologies. And it's, to be honest, I think it's still open to see who will win the ultimate race to produce the ultimate quantum computing hardware. Yeah? But let me start just to stress again the journey that led us to where we are today. Yeah? I mentioned before, quantum mechanics, like described by Garry, started almost exactly 100 years ago. Yeah? So it took, it's important to keep in mind that from some basic understanding from nature, yeah, how atoms, molecules, photons, electrons work, yeah, to building quantum computers, it took 100 years. Yeah, so these are not things that happen overnight. Yeah, you see also the quantum mechanics were developed in the 20s. It was only in the late 40s that people like John Bardeen and his colleagues developed a transistor. Yeah, and these days there are millions of transistors in your phone. Yeah, hundreds of millions of transistors in your phone. Yeah, so it took a long while to develop this, and it took even a longer while to develop this second quantum revolution based technologies. Yeah. As I mentioned in the introductory comments, in the 80s, Richard Feynman, this gentleman, yeah, he sort of had the vision. Yeah, he understood that there was potential to exploit the spooky properties of quantum mechanics for technology. Yeah, but we didn't have the technology yet at the time. Yeah, it took a long time. Yeah. In the mid 80s, people like David Deutsch developed the really high level theoretical framework to build quantum machines. Yeah, let's call them this way. Yeah, and 10 years later, Peter Shor, that Garry also mentioned, was the first one to invent an algorithm that such a machine could perform if we had one. Yeah, and that took another 20 years for prototypes of small quantum computers to be built. Yeah, so it's a long journey that required the efforts of many individuals, of many teams, lots of funding, and so on and so forth. Yeah, so it's not something that happens overnight. Yeah, but what is quantum computing? Yeah, some people call it quantum information processing. Yeah, but essentially the basic idea is that information is stored, processed, and transmitted, yeah, communicated using the laws of quantum physics, using the strange, funny laws that Garry introduced. And this is what we understand under quantum computing and quantum communication. Yeah. How does it come about? And I don't want to scare you. This is just a very simple mathematical introduction. Yeah. So you're well aware of the bits 0 and 1. yeah, that the basic units of information theory. Yeah, either there is a piece of information or there is none. Either there is a current or there is none. Either the switch is on or the switch is off. Yeah, that's how classical information theory works. Yeah, 0 and 1. Yeah, in quantum physics we also have zeros and ones. Yeah, but to distinguish them from the bit, yeah, we put the 0 and 1 in these funny brackets. Yeah, and this is a notation that that goes back to the 20s of the last centuries, invented by Paul Dirac, who was one of the founders of quantum mechanics. Yeah, and this quantum mechanical 0 bit, yeah, is an object that's a little bit different from the 0 because it's a vector. Yeah, it's a kind of a unit vector. If you think of a two-dimensional plane, it is a vector pointing to the on the y-axis. Yeah, for instance. Yeah, and 1 you could think as a vector pointing along the x-axis. Yeah? So this is the what physicists would call a quantization procedure. Yeah? A very simple way of going from the classical world to the quantum world. Yeah? So you see the quantum world is already, from just by looking at the object, yeah, it's a little bit different animal. Yeah. And because of what Garry told us about the wave properties of quantum objects, yeah, it has even further crazy properties, yeah, that you can take this object and add it to this object, yeah, and that is also a legal quantum bit, yeah. Classically, either it's 0 or it's 1. There is no in between, yeah. But in the quantum world, yeah, the 0 qubit and the 1 qubit can exist in a superposition state, yeah. And the superposition is even crazier, yeah, because these numbers alpha and beta that I can multiply, the 0 qubit and the 1 qubit, yeah, can be complex numbers. Yeah? So there is an imaginary unit somewhere in here, yeah. And this is what causes all the mysteries, all the mysterious, spooky things of quantum mechanics. Yeah. So there is a very nice way of imagining, of picturing, imaging the quantum bit. Yeah, the classical bit 0 and 1 you can image as a switch. Yeah, if it's if there is no current through the switch, it's 0. If there is a current, it's 1. Yeah, the quantum bit we can represent on as a vector that starts in the origin of a sphere and points to the surface of a sphere. Yeah, so that the 0 qubit is at the north pole and the 1 qubit is at the south pole. Yeah, but the crucial thing is that all points on the surface of the sphere are legal qubit states. Yeah, so the qubit, the quantum version of the bit, can be any vector that goes from the center of the sphere to the surface of the sphere. Yeah, and that's where you already see that it's a completely different game, classical and quantum computing. Yeah, because you have many more possibilities to manipulate your quantum bit. Yeah, and that is where all the power of quantum computing comes from. Yeah, so there are fundamental differences between classical and quantum computing. Yeah, I won't go through all of them. Yeah, the first one I discussed is that the 0 qubit and the 1 qubit can exist in a superposition state. Yeah, so the qubit can be 0 and 1 if you want at the same time. Yeah, with various weights. Yeah. When you measure the quantum bit, as Garry indicated, you change the state of the system. Yeah, because once you measure the quantum bit, the result can only be 0 or 1. Yeah, during your calculation, your qubit can be anywhere on the surface of the sphere. When you finish your calculation and measure, yeah, there are only two possibilities. It's either in 0 or it is in 1. Yeah, and this is part of the rules of quantum mechanics. Yeah, and to make things even more complicated, yeah, the results of your measurements are probabilistic. Yeah, so you know that with a certain probability you will measure 0, and with a certain probability that follows from the rules of quantum mechanics you will measure 1. Yeah, so it's completely different from the deterministic results that we are accustomed to in classical computing. Yeah, and okay, I will skip the rest because I'm just worried about the time now. Yeah, so we have the qubits, yeah, and I just want to show you how you can manipulate the qubit, yeah, because the quantum bits of information we need to manipulate, yeah. So since the qubit, let's give a look at the qubit 0, yeah, and we want to negate the qubit 0, yeah. So and we know if we negate 0, the result must be 1, yeah. But how do we get from this 0, which is 1, 0 vector, to this 1 that is 0, 1, yeah? And it's very simple, because this not operation, the negation, we can represent as a 2 times 2 matrix, yeah? So now you see the basic functionality of a quantum gate, yeah? So the qubit states are vectors, yeah, and the quantum gates are matrices, yeah, that have some specific properties that we don't need to go into now, yeah. But this is just an example of a legal quantum operation on a qubit, yeah. And there are many more such operations, yeah. There's not only the knot, there is also the spin flip, the phase flip. There is a very important one called the Hadamard gate that let's skip the details, but you see from here what the Hadamard gate does is something very unique, because it takes the 0 qubit and it maps it into a superposition of 0 and 1. Yeah, so this is a very quantum gate. Yeah, but I don't want to bother you with these things, and maybe let's skip this. Yeah, the point is that quantum computers also have a kind of a full stack model like classical computers. Yeah. If you want to build to set up a company that builds quantum computer, yeah, you need first of all to know about algorithms that can solve problems, yeah. Then you need to transform the algorithm in quantum circuits, yeah. And Garry gave you an example as well. Then you need a compiler, a quantum compiler that takes the quantum circuit and transforms it into language that the machine can understand, the quantum processor, and then you can measure and get your result. Yeah. So this is the approach is very similar to classical computing. Let me skip this because I'm speaking too long now. Yeah. In the meantime, there is lots of software already for quantum computers. Yeah, because as you know, even if you want to write a code in Python on your laptop, you need a computing language. Very often it's Python, and for quantum computers it's exactly the same. Yeah. There are very powerful adds-on packages that you can import in your Python code, and that allow you to run or simulate a quantum computer on your laptop. Yeah. Or if you have access to a real quantum computer, you can just send your job in the cloud to be processed by a real quantum computer. Yeah. So at the moment, these days, yeah, we have only access to what people call noisy intermediate scale quantum computers, yeah, because our technology allows us only to build quantum computers that have, let's say, between 50 and 100 qubits, yeah. Ideally, we would like them to have millions of qubits, yeah, but at the moment, the technology is only that far, yeah. And these quantum computers that we have at the moment in the cloud, yeah, we also call them noisy, because we don't have enough qubits to do error correction. Yeah, you know, even classical computers do errors, but there are algorithms in place to pick up the errors and correct them as you do your calculation. Yeah. So that this is the status of the technology at the moment. Yeah. Since a few years, there have been many efforts to find examples where quantum computers can beat classical computers. Yeah. And just a few years ago, in a collaboration between NASA and Google, such a result was reported. Yeah? So that was the very first example where the claim was made that quantum computers can beat by orders of magnitude classical computers. Now, the claim at the time was that what a classical computer could do in hundreds of years, a quantum computer could do in a couple of 100 seconds. Yeah? Of course, this classical computers also get better as time evolves, so maybe this ratio is no longer very accurate, but this was the very first time that the claim was made that a quantum computer can beat hands down a classical computer for a very specific, maybe artificial problem. Yeah? And we know, like Garry mentioned, that there are several algorithms where quantum computers can beat classical computers, yeah, from search algorithm to integer factorization, Fourier transforms, and so on and so forth. And this is what explains the hype about quantum computers. Yeah? But the real reason why people are excited is, of course, is because there is the hope that this quantum computer will be able to solve problems that are relevant for us. Yeah, and there are many industries, yeah, that might profit from quantum computers. Yeah, from the chemistry industry to logistics, information technology, machine learning, finance. So there's a whole array of applications that are being developed at the moment, where quantum computing has the potential of improving our computational approaches to complex mathematical problems. Yeah? So, and that's where the opportunities lie for young people. Yeah, because one day, if you work in one of these industries, you will have to program quantum computers to find the relevant solutions. Yeah. So, and I think this was the last slide of my brief introduction to quantum computing. Yeah, and I would suggest, because I see we are running a little bit late, yeah, that we move on to the next presentation by Dr. Yaseera Ismail, and maybe towards the end we will go back to all the questions that you already posted in the Q&A. Yeah, so Yaseera, please. You see, you're just sharing your screen. You're welcome to start your presentation.
Thank you, Francesco. So as Francesco mentioned, today I have the task of introducing you to quantum communication, which is one of the major pillars in this quantum information and the second quantum revolution. And so to give you an understanding of what quantum communication is, we have to start with how do we communicate from a technology standpoint. We know that we use laptops, cell phones, tablets, and we send emails, we have different apps. But what is important to note is that every time you send information from one point to the next, you have to ensure that that information is secure. And so you have to ensure that information is then encrypted. So how do you encrypt information? And I'm going to start off with something very simple. So say you want to send a text, and I unpack only the word hello for you. So if you send the word hello from one point to the next, I send this via, say, an SMS from my phone to your phone, you will see the word hello. But what is happening in the background? Each alphabet of this word hello is made up of a string of binary bits of ones and zeros. And so what you need to know is that in order to just encrypt this word hello, you have to generate a key that is as long as these bits that make up this word hello. And so how do you then encrypt this word? And what do I mean by encryption? Well, Garry explained factorization to us. Currently, classically, data is encrypted using mathematical algorithms. And in order to break a mathematical algorithm, you would have to try and factorize a very large number. So how does this work? Well, let's start with a very simple example. You have a sender and a recipient, and you want to send this message to the recipient or a receiver. Now, you want to ensure that your message reaches the recipient without a third party stealing any information or getting the plain text or the message that you are sending. So here's your information, the plain text that you want to send to the recipient or the receiver. And you want to ensure that this message stays secure. So you have to encrypt this plain text. So you have to create a key, and this key is made up of strings of ones and zeros that you then apply to this plain text in order to create what is known as a ciphertext. So now, once you have a ciphertext, a person that is actually listening into the channel cannot actually get enough information because this message is unreadable. Only a person with a key can then decrypt that ciphertext to obtain the original message. So what do I mean by unreadable? Well, say you have a plain text which says mission starts, and you have this key which you apply to this plain text. You will obtain a ciphertext. It is completely unreadable. So any person without the key to decrypt this will not be able to decipher what the original message was. Only once you have a key that can decrypt that message, you can then obtain the original message which says mission starts. So keep this in mind. This is what classical encryption is all about. Taking a key, applying it to some message to render it unreadable to any unauthorized parties. Only a person with the ability to decrypt that message will know what the original message was. And that is how classical encryption works. Now, currently, all these encryption techniques are based on mathematical algorithms. But we just heard from Garry as well as Francesco about the development of quantum computers as well as more advanced resources in terms of computing power. So if we have a universal quantum computer, and what I mean by a universal quantum computer, meaning a computer that can do error corrections, then one of the things that quantum computers do best is factorize large numbers. And so all our current encryption techniques that are based on mathematical algorithms becomes obsolete. And so we have to look at alternative methods to encrypt information. And that is where quantum communication plays a vital role. So to unpack quantum communication, I'm going to start off with looking at the laser, because the laser is the key component or one of the key components to actually generating a quantum communication system. So unlike classical encryption, which is based on mathematical algorithms, quantum communication is based on a physical system. So imagine you have billions of quantum particles, which are known as photons. Now, in order to actually implement a quantum communication system, you have to manipulate just a single photon. And what do I mean by manipulating a single photon? You would have to encode a single photon to be either a representation of a bit of 1 or 0. So it has to be a qubit. And so by implementing or manipulating just a single photon, you can develop a quantum communication system. So let's look at what the system looks like. So here you have your transmitter Alice and your receiver Bob. And so you have to manipulate a single photon to either transmit as either being a bit of 1 or a bit of 0. And now you have to get this photon from Alice to Bob. So you have to transfer it through what is known as a quantum channel. And so this quantum channel can be either free space or fiber. And I will explain how this happens in a few slides. But what is important is that Alice has to transmit this bit to Bob. Bob then has to measure this bit or this quantum bit that he receives. And by doing so, they can generate a string of bits. And the string of bits that then can be used to encrypt information. So let's see what happens if we have to transmit this over a quantum channel. Here's Alice and here's Bob. Remember, I depict it as 1s and 0s here just because it makes the animation easy to run through. But this is not just a classical bit, but this is a quantum bit. And so you got this quantum bit that is transferring through this quantum channel. And once Alice and Bob have the same key that is secure, then they can use this to encrypt information. And so this is the most secure way of ensuring information is foolproof and cannot be hacked. So you could ask me a question and you could say, okay, what happens if there is a hacker in the system? So in a quantum communication system, there can be a hacker named Eve. But what we do is we have to ensure that Eve obtains very little information, if not no information, of the bits that are transferred through the quantum channel. More importantly, in quantum communication, it is just the key distribution. So the message is not sent with the key. So if the eavesdropper obtains enough information from that key that is being distributed, then Alice and Bob, through the laws of quantum physics, will be able to track these, to track that if it's in the system. And so they can throw away this string of bits, and then they can restart the process. They lose no information because up until they don't obtain a secure key, no message is actually added to this key. Okay, and so that is what quantum communication is. So let's look at this from a practical point of view. Remember, I said that in order to transmit this key, you have to transfer it through a quantum channel. And so this quantum channel can either be optical fiber or free space. And we all know what optical fiber is. We know there's a rapid development to bring fiber to the home. And so if we look at an quantum communication system that is based on optical fiber, and in this system, we're looking at using an entanglement source. So Garry explained what entanglement is, and he said, okay, we have these two wave functions, they interact, and now they have this superposition of being either red and green. In quantum communication, they have the superposition that they can either be in a state of bit of 0 or a bit of 1. And so when this wave function is transmitted, and if Alice measures a bit of 0, then Bob will measure a bit 1. And at the end, Bob will flip his bits and he'll have the same key that Alice had. And so this is how you can transfer information across an optical fiber. To keep it generic, I don't talk about all the subsystems in there, but that's just a general idea of how quantum communication works. Now, South Africa had its first practical quantum communication during the FIFA World Cup. And it was one of Francesco's postdocs, Abdul Mirza, that was part of the quantum research group at the time, that implemented this, where he ensured the security of the transmission during the FIFA World Cup from the Moses Mabhida Stadium to the main hub. And this was based on fiber-based systems, and these devices was bought from a company called ID Quantique that sells fiber-based QKD devices. So you can see that these commercial systems are practically available, and they're off the shelf since 2010. So this is fiber-based quantum communication. More importantly is the drive to also push free space quantum communication. So what do I mean by free space? Imagine I take a single photon and I send it through the atmosphere. Well, on one end, I can have a transmitter, and the other end, the receiver. And the whole aim is at the receiver point, I must be able to measure the single photon that was transmitted. The longest quantum link from point to point in free space currently available is the 143-kilometer link between the La Palma Islands and the Tenerife Islands. Here, Alice on the La Palma Island sent single photons to Bob on the Tenerife Island, and they were able to generate a secure key. So this is the longest ground-to-ground quantum communication system that has been implemented. However, since then, there's a move not to just focus on ground-to-ground communication, but to shift this to also satellite. And there is this immense drive now to develop satellite-based quantum communication systems. So what I mean by satellite-based systems, you can either have a quantum payload on a satellite, and so you can send single photons from the satellite down to the ground station, or the vice versa, where you have an uplink, where you can send single photons to a satellite and back again. And so you can generate this kind of satellite-based quantum communication system with encrypt keys. Now, the reason why satellite-based quantum communication system it has an advantage over just ground-to-ground is because in the atmosphere, we have atmospheric turbulence, and so this affects the transmission of single photons from point to point, but this is negligent in space, and so we can transmit at longer distances using satellite-based quantum communication. So if we have to look at currently the world record in terms of satellite-based quantum communication, the Chinese, the group of J.B. Pan is leading in this development. They have launched the first quantum satellite known as the MISCUS satellite, and they were able to transmit single photons across a distance of 7,000 kilometers. And they implemented this between them and a group in Austria, where they had a ground station in China and Austria, and they used the meniscus satellite to transmit single photons across the several thousand kilometers. Now, this is quite interesting, and the reason why is because we want to eventually develop what is known as a quantum network. And in order to develop a quantum network, we have to focus on these technologies, not just being able to transmit single photons from fiber to one point to the next through fiber or through free space, but to have an entire network of satellite free point-to-point free space as well as fiber-based communication. And so the current state of the art is that China is leading in these developments. They have this meniscus satellite that they can transmit single photons to ground stations. They also have their quantum backbone project, which is a fiber-based quantum communication system. This is a system that runs 2,000 kilometers between Beijing and Shanghai. It is one of the longest quantum fiber-based quantum communication systems in existence. And they have been able to develop this integrated quantum network by just having their satellite as well as their fiber-based systems integrated. Now, this is not just fundamental research. These systems are currently being used in China by different sectors, the telecommunications sector, the banking sector, to ensure the security of information. And so quantum communication is the next realm of ensuring the security of information and the ability to actually transmit or develop a quantum network. Now, the reason why we're going this, and I will end with this slide, is that we want to eventually develop what is known as a quantum internet, which Francesco already alluded to. And in order to develop a quantum internet, we need to be able to basically network quantum communication systems, quantum computers, and the optimistic aim is that by the year 2035 plus, researchers foresee that we might be heading towards the development of a quantum internet. But to develop a quantum internet, we need a lot of more development into this area of satellite-based quantum communication. And right now, fiber-based quantum communication systems are commercially available off the shelf. However, there's a lot more development required in free space quantum communication for the realization of what is known as a quantum internet. And so there's always future perspectives here to get involved in this field and to be able to develop these satellite-based quantum communication systems, which will eventually allow us to not only link quantum communication, quantum key distribution, but also quantum metrology systems, so quantum sensors, to develop this entire quantum internet and quantum network. Thank you.
Yeah, thank you very much, Yaseera, for this really nice introduction to quantum communication. And before I ask Betony to give us her presentation about quantum effects in biological system, I would like to encourage all of you to please give us a quick feedback by answering the simple questions in the poll that should have opened up on your screen. Please do so, because it's very important to us to receive some feedback so that we can plan better events in the future to accommodate your constraints in terms of time and interest. So Betony, please, I can see your screen. Perfect. Now it's in full view mode. Thank you very much. You're most than welcome to start. Betony, we can't hear you.
Sorry, I lost the unmute button.
No problem, here we go.
So I've been asked to tell you what quantum biology is, which is still an open question. Many people think it's just another iteration of biophysics, but then other people think it deserves a category of its own. I'm not going to waste too much time on this debate, but I'd rather tell you why I think it's a really interesting topic. So you'll have heard a bit about quantum physics in the earlier talks. You'll have heard about photons, atoms, electrons, and the quantum rules that they follow, and how they can be useful, for example, in quantum computing, quantum communication, quantum information. So quantum biology follows the same logic, but instead of looking at quantum systems in computers, for instance, it looks at things like photons, electrons, and protons in the materials that make up living organisms, like proteins or fats or cells or even the brain. So you might think this is a terrible oversimplification of the complexity and diversity of nature, which is an argument that is often raised against quantum biology. So I thought it would be interesting to see whether we could see whether there's fundamental similarities between biological systems on the microscopic scale. So on the bottom left-hand side of the slide is a simple single-celled organism. I think it's a bacteria. It has a cell body, and then it has those hairs that stick out like a tail, which is called a flagella, that it uses to respond to environmental cues and move towards and away from things. So flagella are powered by membrane potentials, by which I mean just the concentration of charged ions across the cell membrane. And you can change this concentration by opening holes in or pores in the cell membrane to let ions go in or out. And taken together, this is a mechanism for sensing and then reacting to environmental influences. So in the top right-hand corner is another single cell, but this is a nerve cell that collects into groups and makes up the brain, which is maybe the most astonishing of nature's creations. But on a mechanistic level, a single neuron is not so much different to the bacteria. In response to a stimulus, pores called ion channels open, they change the membrane potential. If this potential gets high enough, then the nerves fire and a signal is sent down the tail of the nerve that's called the axon before being processed and resulting in a response to the stimulus. So although we might consider ourselves very far removed from being a bacteria, on the microscopic level, there are some quite profound similarities. Sorry, I can't seem to move to the next slide.
Sometimes you need to click again on your slide. Here we go.
So maybe an even more fundamental question that is relevant to quantum biology is what is life? So there are a lot of theories about how life began, which I won't get into here, but to have life, you first need the molecules that life is made from. So in 1952, there was an experiment called the Miller-Urey experiment that showed you could put a collection of prebiotic molecules like water, methane, ammonium, and hydrogen into a flask. You send electricity through the flask, and what you get are the amino acids that are essential to building proteins that sustain life. And some theories have suggested that lightning maybe played a role as the spark at the beginning of life. But what about places where there's no lightning and where they think life might have developed, such as deep sea vents, where they're localized sparks? And there's some theories that iron pyrite, which you may have heard of as fool's gold, could have acted in this way because it is very redox active, by which I mean it donates electrons. I really like the thought that if this is true, it means fool's gold is infinitely more valuable than gold. But it also means that electron transfer might have been implicated in the very beginning of life. And charge transfer, which I mean the movement of electrons and protons, is still extremely important in biological systems and forms pretty much the foundation on which quantum biology is built. So quantum biology is often thought of being a relatively recent field of research, but the reality is that the founding figures of quantum theory, which you've heard about in a couple of talks, were already thinking about how quantum physics might give some insights into the natural world and into living systems. Schrödinger, who's famous for his wave equation and his cat thought experiment, wrote this famous book called What is Life? That is often said to have inspired the discovery of DNA. Bohr, who updated our model of the atom to include quantum mechanics, gave a lecture called Light and Life. And light was central to the development of quantum theory. The first ideas of quantum mechanics were the result of Planck trying to explain black body radiation and Einstein trying to explain the photoelectric effect, both of which deal with the interaction of light with matter. And biological systems are also made up of matter, and light is fundamental to life, most obviously in the fact that plants turn light into biomass, they photosynthesize. So it makes sense that photosynthesis is one of the primary topics of quantum biology. So I've given you some more general idea about quantum biology, but it's probably useful to look at some specific examples of the research that is being done. As I was saying, a lot of the recent progress in quantum biology has been made in the context of photosynthesis. The first example I'm going to look at talks about energy and charge transport and a quantum phenomenon known as coherence, which takes place in plants when they harvest light from the sun. And what this means is that when energy is transferred between pigments, which pigments are just chromophores, which means they are light reactive, the energy is shared or delocalized over sets of chromophores. And Garry gave a very nice introduction into this delocalization, rather than moving from one chromophore to another one by one. So in the diagram, the chromophores are the molecules shown in the black circle, and each colored smaller circle represents those chromophores that share the energy, whereas between these smaller circles, the energy is transferred classically. So another one of the weird effects that we've heard about is tunneling, where things like electrons and protons can pass through barriers that they shouldn't be able to classically. Tunneling was actually the first observed example of quantum effects in biological molecules known as enzymes. And many biological interactions involve some sort of receptor and a molecule that binds to and activates this receptor, which is often called a ligand. And at the risk of simplification, the lock and key mechanism of binding and activating a receptor is used to explain pretty much everything in biology. The action of enzymes has been partly attributed to the lock and key mechanism, as well as the binding of smell receptors and neuroreceptors. The lock and key mechanism suggests that it's the shape of a ligand that must match the shape of a receptor in order for it to be active, a bit like a puzzle piece. But there's an alternative model for, at least for olfaction or the sense of smell, that uses quantum tunneling. It's called the vibrational theory of olfaction, and it suggests that the vibrational spectrum of a ligand enables an electron transfer to take place, and this activates the receptor. It has met with criticism and is yet to be fully verified. But some suggest that it's actually a combination of this vibrational assisted tunneling and the shape theory. So in this last example, we're less interested in the transfer of electrons than we are in their spin dynamics and how spin dynamics might translate into some sort of chemical outcome. And when I talk about spin, I mean the property of quantum particles that makes them behave like little magnets when they're put in a magnetic field. So when two molecules bind and share their electron, these electrons have to be in a specific spin configuration. This means that spin can have an effect on chemical reactions. And because spin reacts to magnetic fields, this means that magnetic fields can have an effect on chemical reactions. And the most well-known application of this in the biological context is the radical pair mechanism of bird migration. The theory goes that light activates a molecule in the bird's eye, causing an electron to be transferred. This forms a pair of electrons whose spins are arranged in a specific alignment that is called a singlet state. Then, under the influence of the Earth's magnetic field and local nuclear magnetic fields in the molecule, the spin can switch between this first initial singlet state and a different alignment known as a triplet state. And because the singlet state and the triplet state give different chemical products, this means that the Earth's magnetic field can produce different chemical products in birds' eyes and potentially let them see the Earth's field, allowing them to navigate. So one of the main arguments against quantum effects playing a role in biology is decoherence, which describes the loss of quantum effects such as coherence. So quantum effects are very fragile. They're normally observed at very low temperatures because at higher temperatures, the environment around the quantum system is moving too much and interacting too much with the system, causing decoherence. Consider the electron transfers we were talking about earlier. They are happening in these chromophores that are within proteins, and these proteins are vibrating at various different frequencies, potentially disrupting this transfer. But some people have actually suggested that this environment around the quantum system might be helpful in the biological context. And nature is an extremely clever engineer. I think one of the clearest examples of this for me is in how we see different colors. So in our eye, we have three types of cone cell, and a cone cell allows us to see color. Cone cells work when light activates this light-sensitive chromophore called retinal, which causes an electron transfer. But if retinal only absorbs light at one specific frequency, how do we see light of different frequencies? Well, the trick is the protein. The protein that the retinal is embedded in is different. You get different opsins. Opsins are these retinals in these different proteins. And opsin proteins all have the same chromophore retinal, but they have different protein structures. And the protein environment tunes the quantum system in this favorable way. And lastly, I've told you about some of the examples of topics in quantum biology, but the mechanisms beneath these specific examples might equally apply in other contexts. For example, quantum coherence and energy and charge transfer in photosynthesis. There's also been the suggestion that is not specific to photosynthesis, but it is more generally just this question of how you arrange these chromophores in these proteins. It's also been suggested that quantum coherent energy and charge transfer might play a role in neurons and also explain how anesthetics work. Electron transport chains, similar to those in photosynthesis, are integral to the functioning of mitochondria, which are incredibly important in all living creatures. You've heard about the radical pair mechanism of avian navigation, where these spin states allow birds to navigate using the Earth's magnetic field. But in addition to this, there's growing interest in radical pairs in other contexts, such as reactive oxygen species, which cause inflammation and also are used as signaling in biological systems. There's also some suggestion that nuclear spin pairs might play a role in the brain. Quantum tunneling appears to be important in a number of biological processes. So I've talked about enzymes, I've talked about olfaction, but there's also been some attempts to apply vibration-assisted tunneling to the action of neurotransmitters such as serotonin. And we also tried to apply this mechanism to spike protein binding in the coronavirus. So as you can see, quantum biology is expanding its context, but what isn't well developed at all, and what I think is really exciting and has a lot of room for expansion, is that very little of this has been applied to physiology or to the human body and how the human body works or doesn't work, and could lead to new therapeutics and medicines. There's quite a lot of evidence that light has been shown to have quite profound effects on disease, and magnetic fields have been shown to mediate stem cell growth and neurogenesis. So I think quantum biology could contribute quite profoundly to the practice of medicine. And I hope some of you will be interested in pursuing it.
Yeah, thank you very much, Betony. That was really a fascinating insight on quantum effects in living beings. Yeah, no, thank you so much. We went a little bit over time on our planned schedule, but we still have a few minutes for questions. Are there any questions that the audience would like to ask to the panelists? Please, you're also welcome to raise your hand, and we can give you the right to ask your question verbally if you prefer. Yeah. And maybe while you think about questions, thank you very much for answering the quick improvised poll. And my apology, I just realized I made a lot of typing errors, but I just did it quickly. No, thank you very much. It is really very encouraging, because it will really motivate us to organize more such events on Saturday mornings, because it looks like in the busy schedule of learners, Saturday morning is the only empty slot. So. But thank you very much for that. We will come up with a plan and let you know what we can do in future. Yeah. So I don't see any. So let me stop the poll. Stop sharing. How do we do that? Okay, here we go. Sorry, there is a question by Musa Venkosi. Please, Musa Venkosi, I just given you the right to speak. You're welcome to ask your question. Just unmute yourself.
Thank you, Francesco, for giving the opportunity to ask. I don't know if I missed it, but I will ask you this question. When you said only 50 to 100 qubits that are being created currently. So my question is, what is the restriction? What restricts it? Is it the hardware or the software that is being developed currently that prevents it us to create more qubits? And what is the research on that currently?
Yeah, no, thank you very much for this is a very useful question. No, the problem is the technology. You know, Garry and Betony, and I think also Yaseera mentioned the coherence. Yeah, the problem is that the moment you try to build many qubits, yeah, they occupy more space. They become macroscopic. Yeah. The chip on which they are built. And the moment they're macroscopic, the coherence kicks in and kills all the fancy properties of quantum mechanics that you want to build. Yeah, so it's very difficult technologically to build large arrays of quantum bits that preserve the quantum properties that you want to exploit. Yeah, that's why there are still at the moment different technological approaches. Yeah, from superconducting qubits to photonic devices. People use ions, cold atoms, defects in diamonds. So there are many different technologies. Yeah. And it's not really 100% sure who will win at the end of the day. Yeah, but essentially it's an engineering problem. It's a technological problem. There is no problem with the software. Yeah? The software, we have algorithms, and you could run it for millions of qubits, the same algorithm. Yeah, but we don't have them. So it will be a long technological journey. Yeah, but you know, it's like when the first mainframe computers were built in the 40s, yeah, they were occupying vast halls, yeah, because they were so big, yeah. But probably your cell phone is 1,000 times more efficient than those computers, yeah, today, yeah. So it's the same journey, yeah, that we went through for classical computer. We will go through for quantum computer. This is just early days, yeah. We just have the first prototypes, but you know, technology will evolve, and there is no real fundamental reason why it shouldn't be possible. Yeah, so it's just an engineering problem that you guys will solve, hopefully. Yeah. And I hope that answers more or less your question. Yeah, and I see in the chat or in the Q&A there is a question for Betony. Betony, Rifatul asks, what are the most fundamental questions asked by quantum biologists? What mathematical tools are very essential to answer those questions? Would you mind answering it quickly?
Yeah, thanks for the question. I think the question most often asked is a similar one to what Francesco just talked about, is decoherence, is do these effects last long enough to have any measurable effect on the timescales that are important to living creatures. For example, does electron transfer on a picosecond have any result on like the level of microseconds and seconds, which is what nerves are firing on and proteins are being phosphorylated and things like that. So that's a very important one. Another one that I found that keeps coming up is how does this under level of quantum mechanism like electron transfer or spin dynamics, how does it then translate into some signal that the body understands, like a chemical signal, or how does the spin become a chemical signaling state, for instance. As for mathematical modeling, open quantum systems is very important in modeling quantum biology, because quantum biology is an open, biological systems are open systems. They have to interact with the environment. They isolate it, they're going to end up dead. So open systems is often used to model quantum biological systems. That answers your question.
Thank you, Betony. Thank you very much. And maybe a last question. I just gave Chad the right to speak. So Chad, please unmute yourself.
Hello, can you hear me?
Yes, we can hear you. Hi.
Hi, thank you again for the talk. So I have a question which I've been wondering on for a while, and maybe you guys would have a differing opinion on it. So I was wondering, since our current quantum computers and quantum systems, they require very low temperatures and very isolated systems to conserve quantum states. I was wondering, do we see a foreseeable future where maybe we can learn better how to conserve those quantum states and allow them to operate at higher temperatures in less isolated systems, or that we just get really good at isolating those systems and keeping them really cold? So at the end of my question would be, is there a foreseeable future where we have quantum laptops, quantum smartphones, etc., or is it would it probably be way too difficult to keep those small mobile things isolated and cold enough?
I know, thank you, Chad. That's a very nice question. And you know, just to let you know, there are already cell phones that have quantum gadgets inside. Yeah, I think Samsung produces a cell phone for high security standard that has built in a quantum random number generator. Yeah, so you can do quantum stuff at room temperature. Yeah, for instance, the people who believe, and there are companies like Xanadu, PsiQuantum, and others. Yeah, that are heavily investing in photonic quantum computers. Yeah, those quantum computers operate at room temperature. Yeah, so to shoot photons on silicon chips, yeah, you don't need to cool them down to unbelievably cold temperatures. Yeah, so there are various technologies. Yeah, the most advanced at the moment are maybe these superconducting quantum computers that requires the very low temperatures. Yeah, but you know scaling it up to millions of qubits makes it very difficult, because you then need very large fridges in which to put your qubits. So it's not yet obvious what technology will win. Yeah, but there are technologies that operate at room temperature, so that maybe that questions of cooling in future might not be so relevant anymore. Yeah, if photonic technologies will win. Yeah, but you know, I think it's early days, so we don't know. But there are already cell phones that have quantum technology inside. Yeah, and you know, and one day it will be standard procedure, hopefully. Yeah.
Thank you.
Pleasure. Thank you. Okay, I don't see at the moment any urgent questions, and sorry, I'm just concerned about the time, because I'm fully aware that it's a Saturday morning, so we don't want to keep you online more than necessary. Then I would suggest that I thank you all the participants for being with us this morning, and of course I need to thank very much our panelists, Yaseera, Betony, and Garry. Thank you so much for being with us this morning and for sharing your wisdom. And I'm very encouraged by the little poll that we did. It's really nice to see that there's really interest in these things, and that many of you, or most of you, are happy to sacrifice a few hours on Saturday mornings to learn about what's going on in the world of science and technology. And we will make a plan, maybe to come up with a series or something, so that we can address your interest and maybe teach something useful. Yeah. So please stay in touch with us. We will share with you the link to the YouTube video that once it is uploaded. So please share it with all your friends and colleagues. And I see Rene shared the internet address where you can register for our mailing list. So please do so, because then this allows you to receive all the announcements of all our activities straight into your mailbox. Otherwise, just go on the website of NITEX and everything is advertised there as well. Yeah. So thank you very much, everyone. Thank you, Yaseera, Betony, and Garry. Thank you very much to all the participants, and I wish you a good weekend, and hope to see you many more times in the near future for similar events. Thank you very much. Have a good quantum day. Thank you.
Thanks,
Thank you
everyone.
very much. Bye.
Thank you.
Bye-bye.